All right, let's do something a little different today. We're going to shrink down, way down, to the microscopic level to understand something we use literally every second of our lives, but almost never actually see: electricity. I mean, think about it. You walk into a dark room, you flip a switch, and boom, light. It feels like magic, right? But it's not. What's really happening inside that wire is a story. It's an incredible journey, and we're about to follow one tiny particle from the very beginning to the very end. So every good story has a hero, and the hero of our story is this unseen force, the fundamental thing that makes all of this work. So let's meet our hero, the electric charge. You see, electric charge is just a basic property of matter, kind of like mass. It comes in two flavors, positive and negative, and they live by one simple, super important rule: opposites attract, and Lex, well, they push each other away. For our little adventure, we're going to be following a negative charge, an electron, as it tries to find its positive counterpart. And this whole push and pull thing, it's not random. Nope. It's governed by this really elegant, invisible law called Coulomb's law. All it says is that the force between any two charges gets ridiculously strong the closer they get, and it gets weaker as they move apart. This right here, this is the engine driving our entire story. Okay, so our hero has its motivation, but every hero needs a world to navigate, right? For our tiny charge, that world is an invisible map of forces that basically lays out all the rules for its journey. And this map, we call it the electric field. You can think of it like a web of invisible guidelines filling up space, telling any charge that wanders in exactly which way to go and how hard it's going to get pushed or pulled. Our little negative charge can sense this field, and it knows just how to follow its directions. We can even draw this invisible map using something called field lines. It's pretty simple. For a positive charge, the field lines shoot straight out, kind of like rays of light from the sun. They're basically shouting, "Go away," to any other positive charges. And for a negative charge, all those lines point inward, pulling positive charges in. So our hero, being negative, is just desperate to follow these lines right to a positive destination. You see, the stage is perfectly set. So our charge has a destination, it has the map, and it wants to go. But it can't move, not yet. It's got all this potential. It's like a coiled up spring just packed with stored energy, waiting, just waiting for that one moment to be let go. Okay, stick with me because this part is super important. On the left, you have electric potential energy. That's the total energy our little charge has because of where it is. Think of a big boulder sitting at the top of a hill. It has a ton of potential to cause some damage if it starts rolling. But on the right, we have electric potential, what we usually call voltage. That's different. Voltage is like the height of the hill itself. It's a property of the location, not the boulder. A really tall hill means more potential for any boulder you put there. And that's exactly why we can think of voltage as a kind of electrical pressure. It's the steepness of that hill. The higher the voltage, the bigger the potential difference, and the more motivation our charge has to start its journey and get rolling from that high potential spot to a low one. And there it is. The switch is flipped, the gate is open, that potential is finally released. Our little charge, along with billions and billions of its friends, finally makes its move. The journey begins. This massive, coordinated movement, this river of charges flowing together, that is what we call electric current. We measure it in amperes, or amps for short. And get this, 1 amp means that a coulomb's worth of charge is flowing past a single point. That's about 6 quintillion electrons every single second. It's an absolute stampede. But you know, it's never that easy, is it? No hero's journey is just a straight shot. Our charge is trying to move through a material, and that material is full of stuff that gets in the way. It's going to push back. And that pushback is called resistance. It's basically electrical friction. The atoms inside the wire are like obstacles, causing our charges to bump and jostle, slowing down the whole flow. Some materials, like copper, have really low resistance. They're like a wide open highway. Others, like the tiny filament in an old light bulb, have super high resistance, more like a narrow, bumpy country road. And what's so amazing is that these 3 main characters in our story, the push, the flow, and the opposition, are all tied together by one beautifully simple rule: Ohm's law. It just says that the voltage, or the push, is equal to the current, the flow, times the resistance, the opposition. This simple formula is the bedrock of how almost every simple circuit works. Okay, so our charge has faced its challenges, it's pushed through the resistance, but why? What's the point of this whole trip? Well, this is it. This is the grand finale. This is the payoff. See, the whole purpose of this journey is to deliver power. As that current struggles and pushes its way through resistance, it converts its electrical energy into other useful forms, like the heat from your stove or, the light coming from a lamp. That rate of energy conversion, that's power, and we measure it in watts. And we can figure out exactly how much power we're getting in a couple of ways. The most direct way is just multiplying the push, the voltage, by the flow, the current. That gives you the payoff, the power. Those other formulas you see, they're just different ways of getting to the same answer using resistance. It's all about how much work is getting done, each and every second. And hey, this isn't just some abstract idea. I mean, go look at your laptop charger right now. That number you see printed on it, maybe 65 watts? That's it. That's a direct measurement of the power it's delivering. It's the real-world result of billions of these tiny journeys all happening at once. So let's just quickly recap the whole story, start to finish. It all begins with a charge sitting in an electric field. Then, voltage gives it the potential, that motivation to get going. When it does, it creates a current, which has to fight against resistance. And finally, that whole struggle delivers the useful power that runs our world. Simple as that. And through this whole entire process, you got to remember one fundamental law of the universe. No charge is ever created or destroyed, ever. It's all just being moved around. The very same electrons that are lighting up your room right now were just sitting there in the wire a second ago. It's all just a transfer of energy. It's a pretty amazing thought, isn't it? That this entire complex system that powers our whole civilization, it all comes down to this simple journey of one invisible little particle, just multiplied trillions and trillions of times over. And that kind of leaves us with one last question to chew on. If this whole incredible, invisible story plays out every single time you flip a light switch, what other unseen forces, what other amazing journeys are shaping our reality?